Yeah, welcome back. Now we're going to talk about nucleophiles that happen to be hydrides, hydrogen nucleophiles. So some of them you've already seen in the past, uh, such as the case of borohydride. This can come in the form of sodium, lithium. Typically, it is sodium, the sodium salt of borohydride. But the thing to remember about this thing is that although you do have four hydrogens on the central element, only one of them is hydridic. The other three have very much strong covalent character and they don't react the same way. So for each molecule of borohydride, you only react one equivalent of carbonyl. And as long as you're dealing with aldehydes and ketones, sodium borohydride is strong enough a reducing agent to undergo the reduction back to an alcohol. So in the first step, you attack the carbonyl carbon with a hydride, literally from the H with its two electrons. The two electrons of the oxygen to um, go back to that oxygen from the pi system. You end up forming an oxide in the process, and then the oxide is then treated with an acidic enough molecule, usually water, maybe slightly acidic water, to protonate the alcohol. And what that will do is just generate that particular alcohol molecule. Now, you may remember from previous lectures that an aldehyde is going to generate a primary alcohol. A ketone is going to generate a secondary alcohol. And the same thing can be done with aluminum hydride. Um, it is a much more robust reagent and a little more, difficult to handle because it can catch on fire easily. But in general, ketones will be turning to secondary alcohols, aldehydes will be turning to primary alcohols from this premise, right? And you don't have any lone pairs on hydrogen. So any of the acetal formation we were talking about is not an option right here. You don't have any of that. It's basically one single step followed by the protonation or, the protonation linked to the alcohol. So that's kind of the idea. Now, like as I said, you could have aluminum hydride, you could have also debal, you could even have tritibitoxy aluminum hydride doing this stuff. And there's also one last derivative which pretty much has three hydrogens, one cyano group, which works the same way as borohydride, but it's a little bit more stable under acidic conditions. All right, so that's basically it for the hydrogen nucleophiles. So for all intents and purposes, that was just more of a review than anything else. But this one right here, the carbon nucleophiles, this will definitely be new to you. So there's a couple that you have seen. There will be at least one that you have not. So one of the typical ones that involve carbonyl chemistry and nucleophilic additions specifically are the Grignard reagents, right? And a Grignard reagent, just to remind you, you can prepare a Grignard simply by taking an alkyl halide, treated with magnesium under ether solvent. And what that will do is ultimately break apart that carbon halide bonds, creating a carbon ion, as well as your magnesium cation, your chloride anion. And then this collectively is known as the Grignard reagent. So the nucleophilic portion of this is the carbon ion. So this bond right here will be what attacks the carbonyl carbon of your aldehyde or ketone. That will break the pi bond of the carbonyl double bond, basically kicking the electrons back to oxygen. And in the process, you are forming an alkoxide that is interacting and coordinating to the magnesium. So just like we saw with the hydrides, here you also do a protonation to finish the process. The only difference here is that the resulting alcohol you get, you have changed the carbon content. With hydrides, you don't change the carbon content, so that the overall look of the molecule remains the same, going from carbonyl to alcohol. But over here, you do change the overall amount of carbons, right? Because you are literally attacking with a carbon source anyway. So you're adding two more carbons because of the ethyl substituent of your Grignard. And so at the end, you end up with two more carbons after your alcohol unit, right? So your aldehyde now gives you secondary alcohols. If on the other hand you start with a ketone, the ketone already has two carbon connections. The third one will come from the Grignard. So ketones get turned into tertiary alcohols via this route. Aldehydes get turned into secondary alcohols. All right, so that's also kind of review. But now comes the new stuff. This one, as you'll come to know it, is known as the Wittig reagent. And you have to basically know how to prepare this reagent. This will be what actually reacts with your carbonyl ultimately. So the Wittig reagent is kind of an interesting molecule because nitrogen, you probably already got the notion that it's a pretty fair nucleophile. It certainly can attack carbon, bind to carbon, no problem. But phosphorus is an even better nucleophile than nitrogen. So you can actually do something as follows. You could have a phosphine, in this case triphenylphosphine, which out of many of the variations that you could handle, this is actually one of the better ones because first of all, it's a solid at room temperature, and second of all, it's odorless. And it doesn't have high volatility at all. Its volatility is pretty low, all things considered. Decrease the number of phenols to 2 or 1 or no phenols. This thing will guarantee be a very volatile substance, probably liquid. But the thing about them is that just like we have a high propensity for sensing sulfur, in an olfactory system, we also have a huge tendency to sense phosphorus. And phosphines to us smell absolutely horrendous. Like this is one of the worst smells that I've ever felt in my life, and I never want to feel it again. That's how bad they are. Like sulfur smells like crap, but this smells so terrible. Like I feel I'm being, basically fumigated when I come in contact with these things. But anyway, triphenylphosphine doesn't have any of those drawbacks, so it's actually kind of nice in that regard. But it is a good nucleophile. So when you have an alkyl halide, primary ideally, you have a perfect situation for an SN2 reaction, and that phosphorus can attack the primary carbon, kicking away the leaving group, and in the process, forming this phosphonium intermediate, right? And then the chloride sticks around to balance the charges. Okay, now this phosphonium intermediate is not the Wittig reagent, at least not yet, right? This is straight out SN2 reaction producing this ionic molecule. And I mentioned this already, but it is best if you do this reaction with a primary alkyl halide specifically. All right, so what happens though is that because that phosphorus now has 4 bonds and it's technically cationic, the CH bond that is right next to it is rather acidic. I mean, not terribly acidic, but it is acidic enough that you can remove it. And it is acidic enough that certainly if you use something like methyl lithium, which is by all regards a pretty strong base, this is absolutely ideal to deprotonate this hydrogen. And basically, just treating these two molecules with each other will undergo that deprotonation of the phosphonium molecule. The electrons go back to this carbon, and you end up forming pretty much a molecule that contains both a positively charged component and a negatively charged component in the same molecule. This has a very specific name. It is a Wittig reagent, but we also refer to it as a sweeter ionic compound. Now, the Wittig reagent, what you have to realize is that the carbon component with the lone pair, that is the portion that is highly nucleophilic. So that's the thing that's going to be attacking our carbonyl carbons. And also notice that this whole thing is neutral overall because the same molecule contains positive and negative charges. So let me show you what you do with this Wittig reagent, and this will lead us to the Wittig reaction itself. Basically, what this does is it undergoes a series of sigma bond exchanges, which we refer to in the world of chemistry as sigma bond metastasis. And specifically, it happens this way. The oxygen positions itself. So this is the oxygen of an aldehyde. The the oxygen positions itself so that it is in closer contact to phosphorus for various reasons. One, oxygen is attracted to the positive charge of that phosphorus. And also, oxygen is pulling away the electrons of the pi bond towards itself, making the carbon of the carbonyl electrophilic, which means that that carbon wants to position itself close to the carbon ion of the Wittig reagent. So what ends up happening right here is that the carbon ion of the Wittig reagent attacks the carbonyl carbon, and that ultimately disrupts the pi bond. But instead of having them go directly to oxygen, what happens is that that pi bond ultimately moves over to attack the phosphonium cation. And at first you might be horrified of this happening because you already have 4 bonds on phosphorus. So how could you do this? You're going to end up with 5 bonds. But phosphorus is below the second row of the periodic table. So violating the octet rule for phosphorus is not, a capital sin. If it happens, it happens. And here it certainly does happen. So you end up forming this intermediate, which is technically a phosphoxocyclobutane intermediate. And the story doesn't end there, because what ends up happening ultimately is that the single bonds that you see here in this cyclobutane intermediate reshuffle such that the phosphorus carbon single bond migrates to now create a new bond between these 2 carbons. And then the carbon oxygen bond of what used to be the aldehyde migrates to form now an extra interaction between the phosphorus and oxygen. So in essence, you form a phosphine oxide, which is one of the strongest bonds that we know in chemistry. And you create an alkene. Now, the alkene under these reactions tends to generate the trans version. If you have, the option for cis and trans is favor. But this is an amazing reaction because it allows you to automatically change a carbonyl CO double bond, which is pretty strong, for a carbon-carbon double bond, which it is strong, but it's not as strong as a carbon-oxygen double bond. What allows this to happen is that the phosphorus-oxygen double bond is a lot stronger than a carbon-oxygen double bond. So this trade-off is ultimately what drives the reaction forward. This enthalpy is really the secret to this reaction. And this is such an efficient reaction that, people still use this reaction to this day. And it's been known for, at this point, it's probably known by 80 years, if not more. That's the energy of this bond, 575 kilojoules per mole. For reference, an oxygen-hydrogen bond that is pretty strong, it's about 460 kilojoules per mole. So this is about 100 kilojoules per mole, stronger than that. So with all that being said, this is everything I want to mention to you in regards to all the nucleophilic reactions. Obviously, this last one, the Wittig reaction, you may have to keep handy because it will allow you to switch from carbonyl compounds to alkenes. And it might be a much better route of attack to make alkenes than trying to go through multiple, elimination and addition reactions that, we've talked about in the past. So this might actually completely bypass that and get you to your final product. So keep that in mind. Other than that, we'll end the video right here, and I'll catch you on the next lecture series. Bye-bye.